Welcome to our fourth lesson in Chapter 6 on solving systems of linear equations. Our objective today is to continue to use this elimination method. We're going to be solving systems of linear equations that require multiplication before we can use the elimination method. So if you felt really good about the elimination method in our last lesson, I think you're going to feel really good about this lesson. We just need to take one more step. It's a big step, but we need to take one more step in the elimination method before we do everything we learned yesterday. So we're going to just add a prequel to this lesson. We're going to add one step before we can do everything that we were doing yesterday. Okay, so yesterday we said that elimination is when we use addition or subtraction to get rid of one of those variables in our system. So we know what the other variable is and then can solve for everything else using our general algebraic skills. And we said that Mr. Gibbs likes to always add, but here were some hints. If the signs were opposite, but the coefficient was the same number, that we could add these equations together. And if the sign was the same and the coefficient the same, then we could just subtract. Mr. Gibbs always just turned this into an addition problem, but it's up to you. So a review. We said 7x minus 7x was 0. That's how we get rid of this. Mr. Gibbs always added that addition sign, didn't he? Same thing here, but Mr. Gibbs always added this addition sign here because it makes more sense for me throughout the system. If it doesn't for you, then do your own thing. But and here's the thing. Yesterday I gave you very specifically designed equations that had the same coefficient for one of the variables. Now I'm going to tell you today that you can use the elimination method for any system that I give you, but I'm not always going to give you something so pretty. I'm not always going to give you a coefficient that is exactly the same or just has opposite signs on it. For instance, you'll see that there's a 2 and a 3 here. You're going to see that that there is a 1 and a 2 here, but I need one of these to be the same. And if you're in Mr. Gibbs's head, you're saying I need one of these to be the same coefficient with opposite signs in front. Okay, so I can just combine them together, which will eliminate one of the variables. So how do we do that? Well, we're going to use multiplication to just change one of these equations, and not change it. It's going to be the exact same equation. It's just going to look differently. And if you're going to need to ask yourself, can I just change one of the equations and make that the same? Because if you can, that's going to make it a lot easier on you. For instance, I see that if I just multiply this, if I just make this a negative 2 right here, that this is going to work. These y's are going to be eliminated. I notice that I can't do that with here. I can't just change one of these numbers. I would need to change both of the numbers. So whenever we can just change one of the numbers, please do. So I want this to be a negative 2, because if this would have been a negative 2y, then elimination would work, right? But let's make it happen. We said that as long as I do the same thing to one side of an equation as I do to the other, then I can do that, because that's just basic algebraic reasoning. That's our algebraic rule, right? So as long as I do this negative 2 to everything here, that I do this negative 2 to both sides, then I can do that. So let's do that. I'm going to draw an arrow, and when I draw my arrow, I always like to remind myself what I did. I'm multiplying by negative 2. I know that looks like x minus 2, but I'm multiplying by negative 2. And what am I doing here? I'm not doing anything, so I'm just going to draw a plain old arrow. Okay? So I need to multiply everything by negative 2, not just this. So I've got negative 2 times 2. That's going to give me negative 4x. I've got y times negative 2. Well, that's just negative 2y. And I've got 23 times negative 2. Well, that's negative 46. Now you could have just multiplied everything by 2 and then done the subtraction thing. That I don't like that for my mind, but if that works for your mind, go for it. And this one I don't need to do anything to, so I'm just going to rewrite my equation because I like them stacked on one another here so that I can see what I'm adding together really easily. Notice with the elimination method, we really, really, really like to have the variables all on the same side. Does elimination work if that's not true? Yes, but the caveat is that the same variables has to be on the same side. So we usually write it in standard form before we try to use the elimination method, which is why when I have a variable solved for, I always go back to the substitution method. No matter how much I like the elimination method, I always go back to the substitution method in those cases. Okay, sorry, that was a total side note. Negative 4 plus 3 is negative 1x, or just negative x. This goes away, and I've got a negative, what is that, a negative 9 right there. I'm going to divide by negative 1 on both sides. Or basically what we're doing is just changing the sign of everything. Because I've got to have x all by itself, and negative x is not all that helpful for me. Well, what do I do to figure out y? Ooh, this is going to be really nice if I use this first equation, because y is going to be really easy to find. I've got 2 times 9 plus y equals 23. 18 plus y equals 23. Subtract 18 from both sides. And I get y equals 5. Now I've got an x and I've got a y, and you're saying, Mr. Gibbs, don't do it. I'm going to make you check it, because even though you did this with Mr. Gibbs and it's probably right, I've been known to make some mistakes, so we've got to check it. I know you're going to make some mistakes, whoever I'm talking to right now. So please check it at the end so you make sure that you've got your right answer. This is one of those units where, like, it's a lot of work, but there's no reason to get very many problems wrong, because you can always do this. Oh my gosh, why am I writing a y? See, I talk too much, and then this is a 5, isn't it? So this was a 5. So this is 27 plus 10 equals 37. And I've got 37 equals 37. Check mark. And that worked, so I just need to write my answer. X is 9, Y is 5. Box it. Mr. Gibbs can see it really easily. And you're on to the next problem. Oh no! This one's even a little more difficult, because notice there's nothing that I can change about just one of these that are going to make either of these the same. So what am I going to do? I'm going to multiply both equations by their opposites. How can I get this so there's something that eliminates here? We're going to have some big numbers, but that's going to be okay. Now you can say, well, I can multiply this by 3 and this by 4. I already see that these are opposite signs, so let's just use these, and that's going to be really obnoxiously large numbers, but it's going to be okay. I'm showing you right now that no matter what the equation looks like, I can always use the elimination method, no matter how obnoxious that's going to be. I want this and this to be the same. I want these to be the same. So what am I going to do? I'm going to multiply them together and make them 15s. So in this equation, I need to do 3 times 5. And in this equation, to make this 15, I need to do times 3. So if I do this times 5, I get 20x plus 15y equals 40. 3 times 3 is 9x's. 5 times 3, oh good, that's 15. That's what I wanted, right? And then 23 times 3, well, that is negative 69. Now, I don't need to look at these equations ever again except for this part. I'm going to go straight back to these original equations after this, but I just need to rewrite them like this so I could do this elimination method. 20 plus 9 is 29, and this is negative 29. Oh, isn't that beautiful, though? How easily that worked once we rewrote those equations. So that rewriting the equations part can be a little annoying. But at the end of the day, it left us something that was really quite easy. X is negative 1. Now, I need a y, so I'm going to take this. I'm going to plug it back into one of my original equations. I don't know why I'm so dedicated to plug it into the original equation. I think it's just that if I, for myself, do a really systematic approach to everything, that I get really good at it, and then I don't make mistakes. So for some reason, I always plug that variable in. That way I know I always check with my second equation. If it's helpful for you to think about it that way, then you might think the same way as me. And that is okay, I think. Negative 1 times 4 is negative 4, plus 3y equals 8, another two-step equation. If you're not good at solving equations by now, which I know you all are, so I'm not worried, this is going to be rough for you. Y equals 4. Circle that, friend. And now I just need to check to make sure that this x and this y work in this second equation. So I've got 3 times what my x is. Well, we said that that's negative 1. Minus 5 times what my y is. We said that was 4. Equals negative 23. This is going to be negative 3 minus 20 equals negative 23. That is true. Negative 23 does equal negative 23. Check mark. I'm going to finally write this as an ordered pair. Box it so it's really easy for Mr. Gibbs to see. And we're moving on to the next one. So again, this is where, we've done a few of these together. You're now going to try this on your own and see, how well am I doing here? How much does this make sense to me? I didn't really leave myself a lot of room. I'm going to do this in a different color again so you can see what I'm doing. What's the easiest way to do this? I could multiply this by negative 3 and this by negative 4, but I think this is going to be a little smaller numbers if I do this times negative 3 and this times negative 2. I just want the same number, so if I just multiply these things by themselves, that's a foolproof plan to always getting these equations. So I'm doing this times, and I'll do times negative 3. And I'm doing this one times 2. Notice I just threw in this negative so they would have opposite signs so I could keep my idea of always adding intact. If you wanted to just do this times 3 and then subtract at the end, if you can make sense of that, feel free to. So negative 12x minus 6y equals negative 24. Woo, that's close. I'm glad I wrote those in different colors. 2 times 3 is 6. 2 times 3 is 6. 9 times 2 is 18. Okay, stop and make sure you did everything correct, because it would stink to have this step wrong and have to redo everything, but it happens. So this is 6x's, negative 12 plus 6. That goes away, and this is negative 6. Oh, this works out so beautifully again. X equals 1. I'm going to take this. I'm going to plug it back into my original equation. I've got 4 times 1 plus 2y equals 8. I'm looking for y right now. Two-step equation. y looks like it equals 2. Well, we've got to check our work, though. So we're going to take this second equation, and we're going to plug in our work. So I've got 3 times 1 plus 3 times 2 equals 9. 3 plus 6 is 9. Yeah, that's definitely true. 9 is 9. Okay, so we just need to write our final answer. My x is 1, my y is 2, box it, and we're moving on. Okay, example 4. These are long, aren't they? So continue to work through it on your own and come back and see what we're doing. I see different signs. For me, that signifies where I'm going to go to do this. I could multiply this by 5 and this by -2 or something like that. But I'm going to go ahead and multiply this top one by 3 and this bottom one by 5. Ooh, I'm going to need to slant my arrows down here slightly. So I'm doing times 3 up here to get this to 15 and times 5 down here to get that to 15. So this whole thing times 3, I get 6x plus 15y equals -33. And this whole thing times 5, I get 25x minus 15y equals 19 times 5. Well, 5 times 20 is 100 minus 5. That must be 95. Okay. So I am adding these two equations together to eliminate one of the variables. I've got 31x. That goes away. And I've got 95 minus 33 is 62. Oh, that is just beautiful again. Whatever math teacher made these equations was really nice to us, never giving us fractions. Now here's a big question. Can we have fractions? Yes. Most solutions to systems of equations are fractions. We just, when we're learning this, it's so many steps already that math teachers tend to be a little nice and not give you too many fractions. But will I give you fractions? I mean, definitely I will eventually. At the same time, I think most of them are going to end up being whole numbers. Okay, I'm plugging it in. 2 times 2 plus 5 times y equals -11. 4 plus 5y equals -11 minus 4 minus 4. And I get 5y equals -15. Divide by 5. Y equals -3. Circle. What do we need to do? We need to check our work. I'm plugging into the second equation. We think x is 2. Minus 3, and we think that y is -3. And this should equal 19. Well, 10 plus 9. Ooh, I was scared for a second. But a -3 times a -3 is a +9. 10 plus 9 is 19. True statement. Let's rewrite our answer as an ordered pair. I get an x of 2, a y of -3. This is where they're going to intersect on a graph, or this is the only x and only y that give us a true statement for both of these equations. So we obviously have a problem on the back here. Well, actually, since it's one problem, I think I'm just going to do it real quick with you. That's going to make this video a little longer, but it will allow us to do something else as a warm-up tomorrow. So I am going to multiply. I'm going to get 15 here again. I could do something to these. I could end up at 12. Well, let me show you that. As I see these, I would just make these 15. But let's make both of these 12, just so you know that sometimes you don't have to multiply by each other. We're just finding the least common multiple here of 6 and 4, which is 12. You could make them both 24. That's still going to give you the same answer. But in order to make this 12, I'm going to do times 2. In order to make this 12, I am going to do times -3. I'm going to do -3 because I want them to have opposite signs. So times 2, I get 12x plus 6y equals -6. I'm multiplying by -3, so I get -12x. -3 is minus 15y equals -3. So 20 times 3 is 60. Minus 3 of them is -57. I'm adding these things together. These go away. This is -9y equals -63. Divide by -9. Divide by -9. And this is y equals 7. Plugging it in, I get 6x plus 3 times, we said that y is 7, equals -3. 6x plus 21 equals -3. Subtract 21 from both sides. I get 6x equals -24. Divide by 6. X equals -4. I've got an x and a y. I just need to check with my second equation. My second equation says 4 times whatever I think x is. I think it's -4. Plus 5 times whatever I think y is. I think it's 7 equals 19. -16 plus 35 equals 19. 19 does in fact equal 19. Check mark. My answer here is 7. I didn't do that right. My answer here is -4. That's my x value. 7. Box my answer. I hope you enjoyed solving systems of linear equation using the elimination method. All of the steps. Let me know if you have any questions, and I will see you tomorrow.